My name is Professor Kevin Pimblett, and I will be chairing this next session. Our first speaker is Koorosh, talking about safe large language models for wind farm maintenance, or otherwise SafeLLM.
So, as Kevin kindly mentioned, I'm Koorosh Aslansefat. I'm an assistant professor at the University of Hull in computer science, and I'm mainly working on the AI safety. We have been publishing some, let's say, methods and, let's say, packages around, let's say, safety and, let's say, safety of machine learning. And nowadays, we are, let's say, working to see how we can make LLMs or large language models safe. And our method SafeML has been, let's say, referred in German industry for automotive, let's say, autonomous driving systems. So to start with, I'm going to talk about safe large language model for wind farm maintenance. And it was a project that we did with EDF Energy, that is one of the large kind of, let's say, companies around, let's say, providing energy, and it has a lot of, let's say, wind farms in the UK and France. So to start with, I have some highlights on offshore wind energy, and then I will go to talk about maintenance in offshore wind farms, and then talk about, let's say, SafeLLM concept. So to begin with, we know that the wind energy, specifically in the UK and EU, are, let's say, growing very fast. And I know it is happening in the India and China as well. And for example, the target from Europe Wind Energy, let's say, Association is to reach, let's say, 250 gigawatt of, let's say, capacity by 2030. And we know that the costs associated with the operation and maintenance of these wind turbines are between 10 to 15% for onshore, between 25 to 30% for offshore, and more than, let's say, or up to 35% for wind farm approaching the end of life. So there is a huge cost to be reduced in the wind energy. And if we want to see the whole scale of, let's say, development, construction, operation and maintenance, and decommissioning, you will see that 25 years of the kind of the whole lifespan of a wind turbine or wind farm is dedicated to the operation and maintenance. So it's a huge part of this kind of, let's say, cycle. And we know there are a lot of, let's say, European projects that are trying to, let's say, reduce the cost of, let's say, maintenance. And I have a picture of them, that how long these projects are and what is the budget. And you can see they are starting from, let's say, something like 0.24 million to 32 million euros to, let's say, do some research to reduce the cost of operation and maintenance. And I want to discuss about the case study that we had. So we were working with EDF Energy, and we received data from a wind farm in Teesside that is in North England. And this wind farm has 27 turbines, all between 2 to 3 megawatt and total 62 megawatt of capacity. And we had data from 2013 to 2018, and the data was about, let's say, alarm records, text, duration, sequences. We had all the repair records, actions, duration, and types. We had failure types, categories, O&M reports, and decisions. And we had the process as well. We know that, for example, every time that there is a wrong issue or any kind of, let's say, warning or error in the turbine, it will be monitored by a diagnosis center, and then a team will decide that, okay, what should be repaired. They have early morning brief. They will have a preparing, let's say, procedure to sail, and then they go and do the daily operation. And based on the weather, let's say, availability and other accessibility of the wind farm, they do the maintenance. So one of the questions that we had was that, consider you are sitting in this room and you have big screens monitoring the wind farms. And what happens if let's say, turbines go to red? So you may see that it is happening. So we were recording that in one single day, there were 590 alarms in 22 of March 2013. That was, let's say, maximum record of alarms that we have. Imagine you are the operator of that, let's say, wind farm, and you see everything is red. And the process that we see is that it's kind of manual. So the O&M manager should see the alarms and decide what should be the maintenance. And it is very difficult, specifically if you are not expert in this domain or you are starting your job there. Again, we have another, let's say, phenomena in 2017 that we had 493 alarms a day. So it was another, let's say, red day for them, that they needed kind of, let's say, a assistant to help them to, let's say, solve this issue. And the other thing that I noticed when we were kind of, let's say, investigating the data, we had some minor alarms or minor, let's say, issues that took 45 days to be solved. Consider you have one turbine is off for some alarms or some kind of malfunctioning, and they are waiting 45 days. And each day there is a cost associated to that kind of, let's say, unavailability. So we were thinking that, okay, how we can solve this issue? The first thing that we did was to create a Markov model. So here we have a Markov model for alarm number 16. So in this model, we have 135 different states, that is each alarm. And we were kind of, let's say, mapping that probability of, let's say, if you have alarm number 1, what is the probability of having alarm 2 as the next sequence? Or what is the probability of having alarm 3 as the next sequence? So we were calculating that probability based on the data that we had for 5 years. And if you want to do it for the whole wind farm, it is more complex. You have 300 alarms and you have those, let's say, relation between them. And the thicker, let's say, line that you have, it means that the probability is higher for that specific state. And based on Markov model, we were being able to, let's say, calculate the most probable sequence. But the idea that we had was that, okay, we have these alarms, how we can do the human-wise clustering. And we did the clustering, and based on the, let's say, understanding that we gained from these clusters, for example, we could say, okay, these are the alarms for generator, and if you go inside the generator, you have another hierarchical Markov model. And you could be able, let's say, to see these kind of probabilistic model. One thing that we did in the past was to feed the, let's say, alarm actions as the input and get the repair actions at the output. So we had some kind of pre-processing, like removing chattering alarms or converting the, let's say, wordings that we have to the kind of, let's say, embeddings and so on. And on the other side, we had also some kind of action to reduce the noise in the repair actions, or let's say map those, let's say, repair actions words that we had into the embedding, and kind of, let's say, having actual recommended needed actions. So the work has been published in this paper that I'm citing here. And we anonymized the data that we had for a single day. So here is the Excel file that we had for a single day. So we had some kind of repeated alarm that needed to be kind of, let's say, cleared. We had some kind of alarm caused by manual action. So whenever you send a team to do the manual, let's say, maintenance, they are turning off the turbine, and there are some alarms kind of, let's say, corresponding to those actions. So we needed to, let's say, remove those alarms as well, because you put the, let's say, turbine on, let's say, idle and do your maintenance. And on the other side, we had the repair actions. I just anonymized the kind of, let's say, repair actions, but consider we have a repair action 1, repair action 2, and so on, based on the kind of, let's say, event that we have, and we have the turbine number as well. So one issue that we had, a lot of, let's say, actions, repair actions that we had was only happening single time. So we needed to, let's say, kind of, let's say, merge some of them and reduce these kind of, let's say, inconsistency that we had in repair actions. Even after reducing those inconsistency, we were being only kind of, let's say, capable of doing the repair recommendation for a specific type of repair actions, not all of them. So we were filtering some of them that were more frequent. And by using LSTM, models like LSTM or BioLSTM, we were reaching some, let's say, accuracy around, let's say, 70, 80%. But what happens next was that we were thinking that, okay, how it can be merged with the existing systems. So you have a SCADA, you have CMS in your wind farm, in your monitoring, and how it can be integrated to that one, how it can be integrated to the whole framework of the maintenance. in the offshore wind energy. So we were kind of, let's say, putting all of them together, and this red part was the part that we were kind of, let's say, integrating. Then a year ago, the large language model, the ChatGPT and other things happening were kind of, let's say, very, kind of, let's say, everyone was talking about this kind of large language model, and we were thinking, okay, why not we kind of, let's say, consider this one, and we try to also do something about the safety of this large language model. So we had these kind of issues for different, let's say, newspapers that, for example, the DPD chatbot was kind of, let's say, saying or swearing to the user that I'm useless, or you have the Air Canada issue, and many other, let's say, issues that these chatbots have. And we were thinking that, okay, how we can have this kind of, let's say, repair recommendation for the maintenance of, let's say, offshore wind farms. So what we had as the beginning was to have this kind of, let's say, sequence of alarms that we have. And we wanted to fine-tune the large language model using open source data models like Llama 2 and nowadays Llama 3, and see how it can, let's say, suggest some, let's say, repair actions. And we were thinking that, okay, how we can make it safe. So we were proposing some layers. So one layer was having the security intrusion detection. So we were, let's say, implementing some methods to, let's say, detect any kind of, let's say, security intrusion. So if the user wants or try to, let's say, retrieve some confidential information from the model, we were kind of, let's say, putting a layer to prevent it. We have a hallucination detection that I'm going to talk about it in the next slides. And we had the safety concept detection. So what is safety context, or what is the domain-specific safety monitoring? So imagine any kind of, let's say, large language model has a kind of, let's say, guardrail mechanism that if you say something over 18 or plus 18, it is automatically, let's say, filtered. Or some of them are trained in a way that the model can understand unsafe concepts. But some kind of, let's say, issues happening with in-context safety. So for the wind farm specifically, we have regulations. For example, for offshore wind farm, you cannot go and fix something alone. Always, at least you should have 2 people or 2 repairmen in the wind turbine. Or you cannot, let's say, fix something without turning off the high voltage transformer. So these are the safety concepts that are specific to this domain. So we were kind of creating a knowledge graph and creating a list of, let's say, safety concepts. That, okay, if the answer has anything to recommend, okay, do not, let's say, turn off the high voltage transformer, it is a red or unsafe, let's say, response for us. And these kind of mechanism, or this kind of, let's say, small classifier could, let's say, find those, let's say, concepts, measure the similarity, and filter those, let's say, actions. So that was the idea that we had. And again, we had that idea to use the idea of reinforcement learning to rate these responses based on the kind of, let's say, rewards that the O&M manager could provide us, and how we could, let's say, retune the large language model. And at the moment, we are working on this part because we know that there is an issue with reward hacking and, let's say, the safety of reward hacking. So we were kind of, let's say, preventing to have this module at the moment. So we were kind of, let's say, using very simple, let's say, way of similarity measure. We were using cosine similarity. We were using Wasserstein distance. And we were kind of, let's say, having 10 different categories. So we had the kind of, let's say, emergency procedure. We had the kind of risk assessment procedure and many others. And we were kind of, let's say, creating a benchmark of 1,000 different, let's say, safety concepts to be measured for this specific, let's say, topic. And the paper has been accepted by Journal of Physics, and it is going to be published very soon. So it is what we are waiting to see when it is online available. And regarding the hallucination, what we did was to ask the model to repeat the answer for a same, let's say, input prompt. So if you ask the model to, let's say, repeat the response for a same, let's say, a prompt, you may see some kind of, let's say, heat map or similarity between these kind of answers. So the more, let's say, you have the dissimilarity, the more likely it is to be hallucinated. So we were using some metrics to do the sparsity measure, and based on the kind of, let's say, the similarity that we get, we could, let's say, identify that for a specific, let's say, topic, we had the hallucination and the model. And we did some kind of evaluation in the paper that I mentioned. So to make a conclusion, we developed a kind of conversational agent that recommends repair actions based on alarm sequences. In our current evaluation, cosine similarity usually outperformed Boostertain distance in most tests. This approach could automate maintenance tasks, improve efficiency, and reduce the cost. It also assists it also can be assisted in training, let's say, personnel, not only, let's say, using in the operation. You could, let's say, use it as a tool for training as well. And also, it could, let's say, shift the maintenance practices by automating decision-making using large language model. And not only this one, we could use the same concept for, let's say, healthcare as well. So if we go in context, let's say, safety, if you are focusing on mental health, what are the safe concepts and how we could, let's say, have this kind of, let's say, online monitoring of that large language model to prevent something like that. And again, for the future work, we were kind of, let's say, trying to see if we provide kind of, let's say, reward to system, how we could use this kind of, let's say, monitoring to avoid any kind of reward hacking. Because you know that, okay, if you put something like this in a kind of, let's say, Twitter concept, if people start to, let's say, do the kind of, let's say, toxic conversation, and if you only measure the kind of, let's say, engagement, then the reward hacking happens and the model goes more toxic and more toxic in the loop. So we are going to, let's say, try to have a monitoring system to avoid that. So here is, let's say, a couple of references that I had in my presentation, and thank you all for listening.
Okay, we have time for a couple of questions, please, if there are any. Okay, go over there if there's a microphone, please. Just stand up or put your hand up. There we go.
Yeah, Professor Koorosh, I think that was a nice presentation. You talked about hallucination of these LLMs towards the end.
Mm-hmm.
What is the impact of this hallucination in terms of the outcome, in terms of, let's say, false positive or the cost implication of that?
So the hallucination that we faced was that you put your prompt, and because the model don't know about that kind of, let's say, specific, let's say, question, it start to provide some kind of random answers in a kind of, let's say, convincible, let's say, way. So because we don't want the user to be, let's say, feeded by those wrong answers or random answers, we wanted to make sure there is no hallucination inside these kind of, let's say, responses that we have for, let's say, maintenance. That was the kind of, let's say, intention to have a block form hallucination detection before feeding it to the user.
Okay. So don't you think, with your knowledge from the prior models, let's say that LSTM models, and maybe also based on the knowledge that you gained from the previous experience, don't you think using a model like RAG in combination with your existing model can reduce this hallucination further?
Yeah, actually, what we were showing here, the combination that we had for using the knowledge graph was from the RAG technology.
RAG technology.
I didn't mention it, but yeah, you are correct.
Okay,
we are using the retrieval augmented generation.
Thank you.
Yeah, we know about it. Thank you.
Okay, and I'll take one right at the back, please, as well.
So you're mentioning about guardrails that make this LLM more safer, right? Could you elaborate on that?
So it is a kind of, let's say, guardrail for domain-specific safety. So consider that you have some guardrails. If you say, okay, this LLM, please help me to, let's say, create a bomb or do something, let's say, unsafe. So these models are prevented to provide you the answer. And there are some ways to, let's say, ask them to do, but let's avoid those, let's say, jailbreaks or reward, let's say, prompt injection. But then we have in-context one. So what we saw in, let's say, models like Llama or, let's say, ChatGPT, they don't understand the context of, let's say, wind turbine. When they say, okay, single person can do this maintenance, they don't understand that, okay, based on the regulation, there always should be two person, let's say, as a repairman. Because of that, we want to also consider these kind of, let's say, domain-specific concepts that are, let's say, safe or, let's say, unsafe, to be kind of, let's say, considered for the guardrails.
Right. So the guardrails are both sort of like in normal use cases, we have Llama guard and guardrails in those aspects, right? Are those like that, or they're more algorithmic or more programmatic?
They are more, let's say, general safety concepts. So because you are, let's say, talking about harms and so on, but you are not, let's say, focusing on a domain-specific standards and regulations. And we saw that sometimes these large language models avoid those kind of, let's say, ignore those, let's say, standards. That's why we are trying to, let's say, systematically using expert domain, put these kind of guardrails as well.
Understood. Thank you.
Okay, and we're going to wrap up there, but before you leave the stage, I believe we have a small gift. Okay, Koorosh, this is all yours.
Thank you. Thank you so much.
Okay, thank you. Okay, can I get Xinhui up to the stage, please? Okay, and we have Xinhui talking about net zero and digital twins. Over to you. Thank you so much.
Okay, thank you, Kevin, and hello everyone. My name is Xinhui Ma. It's an assistant professor from University Hall. So the topic is a little bit different. Yes, talk about towards digital twin through physics-informed deep learning for floating offshore wind turbine. So there will be 5 parts. Yeah, and probably I will go a little bit quicker. Okay. Firstly, introduce what is floating offshore wind turbine, and what are the typical failures, and why we need the physical modeling and the physics informed deep learning. Finally, give some examples of digital twin framework. So now we have some examples of floating offshore wind turbine. Why we need the offshore wind turbine? Because you see the near sea it's a little bit cloudy and maybe resources limited. So we need to move to the far sea and to get more resources. And yeah, so here are some examples. You can see the first one is of floating wind turbine from Scotland. Yeah, which is part of the UK. Yeah, and another one is from Norway, a few years ago. Here is some more recent examples, which is from China, Haiyu. Yeah, it's last year and last 2 years. It's a bit far from the sea. It's about from the 140 kilometers. So it's get more resources from there, and more than 100 meters. Yeah. So why we're going to talk about because today topic is net zero. Yeah, net zero is a global issue, so we need to work together and seek and share common knowledges to deal with the zero challenges, including India and globally, UK. So here is some kind of floating wind turbine examples. You can see there's different structures, and the left is the near sea, right is the far sea. There's different platforms. Here is the illustration of the part. If you look at the bottom part, which is floating wind turbine, which is a mooring system, and the framework, which is more focused for floating wind turbine. Here is the example of the structure of the floating wind turbine. You can see from the wind line there's some different parts, which is the structures and also a lot of sensors. and to monitoring the offshore wind turbine. Because it's the far sea, it is extremely costly to monitoring, maintenance, and operating. So we need one way to monitoring and reduce the cost. So digital twin, which is one of the solution to deal with the costly maintenance of the floating offshore wind turbine. So because the offshore wind turbine, there are some failures, a lot of problems in here. Here is some problems, for example, from the gearbox, and which is the key part of transfer the wind energy to the electricity. And also because it's undersea, there's some rusting of the mooring lines. So we need the monitoring and maintenance, the key parts. Here are some examples of the typical factors on the mooring systems. For example, the fatigue and the corrosion and other parts. So here is the structure of a floating wind turbine, include the floating foundations and alarm facilities and the bearings, blades. Okay, so now that's the risks ranked by risks of the components. You can see the gearbox and the frequency converter, the tower, where with the high risks. So here are some particular sensors to monitoring the data. There are some, for example, there's acoustical emission sensors, and also there's some camera sensors. Here is a listing of examples. We can have a vibration analysis from the generator and others. Also, we could have acoustical, ultrasonical sensors, because the digital twin, which is synchronize the physical wind turbine with the virtual turbine. So we need to collect and monitoring all the data at a real time. So now, in order to consider the build a digital twin, we also usually we need a physical modeling or simulation. Traditionally, it's a finite element analysis, but also we can use the deep learning as well. Here is some physical modeling of the floating offshore wind turbine. So that's the structures of the offshore wind turbine. So here is the physical modeling of the blades, which is the big parts, and you can see the forces applied on the blades. And here, that's the modeling of the floating foundation, and which is a hydrodynamic modeling. Now you can see from here, so the partial differential equation, which is the volume fraction, so which is the differential of the volume fraction with the time, which is change the shape change of the little water drops, and plus because the water and the window is blowing, and there will be change of the velocity of the window, and also the floating foundation is moving. So now the difference between the window and the wave with the moving of the foundation, take a differential, we can get this equation. That's the physical modeling. So here is the mooring system modelings. Now, that's the particularly computation demo of floating offshore wind turbine. So here is the recent computation model of the floating offshore wind turbine. Use the edge refinement of the mesh, because the finite element is one of the methods for a digital twin simulation, and added as a real-time synchronized simulation. So here use hierarchical mesh. That's the most recent finite element to solve the equation, the hydrodynamical equations. So now here is the results of the simulations. which is the window. You can see the window resistance and the window floors from here. So now there is a problem of this, even though it's the latest methodologies, that simulation can achieve, but not so excellent in real time, because digital twin need to synchronize the finite element simulation. So the efficiency is very important to the numeric simulation for digital twin. So is any possible other methods to achieve and improve the numerical simulation of that one? We did some work before, similar work, but on different problem. So this is they solve the magnetical and the electrical motor problems. So that they use the HP refinement on non-uniform order. The mesh is adaptive, and also the polynomial order, the mathematical order, is non-uniform. So this is our previous work, which is on computational physics. So now you can see this methodology you can achieve. The mesh is adaptive refinement is better than the hierarchical refinement. So that is a possible way. It is a proposal to improve the efficiency of the finite element for digital twin. So if we can achieve use the finite mesh, and you can use the mathematical polynomial orders from 1 even to 14. That will be the one feasible way to improve. So that's the improve the physical simulation, a possible way. So another way is how to integrate the physics into deep learning. So now you get the physics equation, and here the deep learning can be integrated in the simulation of the partial differential equation. The global matrix G actually can be solved using a numerical network to solve that global matrix. And also, we can take the loss between the PDE and the constraint expression to calculate the errors, the loss, to improve the deep learning. So that's the physics-informed deep learning. So we did something it's possible to improve the performance of the digital twin, which is use a multiple modality deep learning approach. So which is we published on the paper, which is used on healthcare, which is yesterday's topic. But we can change this to multiple modality, include sensor data, image data, and other data to put on this deep learning approach. And also, we can use other methodologies. For example, could be used the GANs. We did this recently to augment the data and improve the data so that the digital twin can get the right and improve the data. Okay, so here is the some framework of the digital twin for wind turbine. You can see you could have the sensor data, and also you can would have the physics data from the equation. You have the monitor data from here, and also you can have the design data. So we put this in the form to get a digital twin framework. So now, finally, what will the digital twin frame looks like? So here is the example of the of a floating wind wind turbine. Okay, I think I have 2 minutes, 3 minutes, or okay, 2 minutes. Okay, so left is the physical floating turbine, right, which is the virtual turbine. So communicated with the sensor data as a real time, synchronized. And also, our work is to add the physics to this model to improve the efficiencies. So now, here is some of our framework in here for floating wind turbine. And here is the groups, there's a lot of tools to build the digital twin for wind turbine. That's the tools. Here are some examples. Yeah, which is a digital twin wind turbine examples. And here's a Norwegian digital twin platform. So now there's some other AR, VR, immersive visualization in our university, in our department. We have a VR laboratory. And here is some work we published for a digital twin framework recently for wind turbine. But it's possible we can improve this to floating wind show of turbine. So here is our work for wind prediction of a digital twin wind turbine, which is also we did recently. So we could put all this together, we can improve. Here is some comparisons of different methods. You can see from here, the digital twin can achieve flowing details and mirroring the digital twin of the flowing fields. Finally, I'll give a summary. So that is we proposed a digital twin framework for floating offshore wind turbine. And also we could use the HPE adaptive finite element methods to improve the finite element efficiencies. And also we could use the multiple sensor data multimodality, sensor data, and physical informed deep learning. So that we could, it's possible, it is a proposal, so we can share this and work, it's feasible to work on this. So it's open, it is open areas. So thank you very much.
Thank you.
Thank you.
Okay, we have time for some short questions, please. Okay, I didn't see whose hand up is first, but we'll go number one, then number two, if I may.
Yeah, that was a nice presentation, Professor. Yeah. What is the computational cost of these models? Because even a normal deep learning model attracts a large computational overhead. So how about these models to train and implement? What kind of computational costs are incurred?
Okay, yeah, so the computation, yeah. So if we use a hierarchical finite elements, actually, if you do the simulation, numeric simulation, you may need to need millions of elements, millions of elements. Each element, you are going to use numerical methods to solve the equations. So which is very costly. And if you use a high performance machine, then the price is goes to up. So that's the computational costing well from. But now if we use the adaptive mesh and a uniform order, we can. If you could look at the paper, yeah, which is the mixed reality, mixed finite element. The paper put in here, yeah, for the details of the. But that's a very good question, yeah, which is the focus of this proposal, yeah. So, but for details, you can look at that paper. Okay. Yeah. Thank you.
Can we pass the microphone along, please? Thank you.
Yeah. Thank you for the presentation. As we all know, in responsible AI, explainability is vital, let's say, component. And having this kind of, let's say, element of physics-informed, let's say, models, how we can use that physics-informed, let's say, models to have a more explainable digital twin.
Yes, that's a really good question. Yeah, actually, if we want to achieve explainable AI or responsible AI, we need to understand the knowledge. If we want to, so the physics, which is the rules and is the knowledge of the domain. So actually, if we add the physics to the explainable AI as a knowledge, so that it's I think it's a good, very good direction in here.
Thank you so much.
Yes. Thank
Okay.
you. Yeah.
Now, before you leave the stage as well, we do have a small gift as well for yourself.
Okay, thank you.
Okay, congratulations. Okay, thank you. Okay, our next speaker, I believe, is online, Dr. Sudharshan, speaking about the application of AI in development of climate action tools. No, you're here. Fantastic.
Okay, so good afternoon, everyone. I'm Sudharshan. I'm a postdoctoral researcher at the Energy Consortium here in IIT Madras. I'll keep my talk fairly high level. We have some results, of course. So just a brief introduction about the Energy Consortium. It's in IIT Madras, it's an industry academia partnership. There are about 50 plus faculty members, several industry partners. And the Energy Consortium oversees a lot of research projects, all of which are united by a central theme of working towards net zero and decarbonization, energy transition, and so on. So my particular group is number 4, energy modeling and risk assessment. So we're a team of students, postdoctoral researchers, and senior scientists. We primarily work towards energy systems modeling. Here's just a overview of all the research projects that the Energy Consortium undertakes, and the ones highlighted in red, which is the bottom 2, decarbonization, energy transition models, AI and optimization. That's the group those are the projects that I work on. So very quickly, why we need energy transition modeling or decarbonization modeling is perhaps explained by this slide. So these are charts that are taken from the IPCC's 6th assessment report. Now what we can see on the left-hand side is that you have the global annual carbon dioxide, GHG actually, greenhouse gas emissions, cumulative. And what the chart basically says is if we need to achieve the target set at the Paris Climate Accords, which is 2 degrees Celsius, or if you're being a little bit more aggressive, then it's 1.5, then we kind of have to already start very severely reducing our greenhouse gas emissions. Likewise, on the right-hand side, similarly, the one at the top, the blue curve, represents or refers to the 1.5 degrees Celsius limit, and it's at the top because it also means we have to go for the most aggressive climate action policies. Now, these charts are typically generated with integrated assessment models. These are aggregate models, typically. They use a lot of assumptions and they connect lots of interdisciplinary domains with each other. But one of the major, let's say, unaddressed concerns of integrated assessment models is granularity. So when it comes to a place where there is a lot of diversity and sectoral characteristics need to be considered, then aggregate models will not be sufficient. We have to break down the problem sufficiently and treat every sector independently, treat every region independently. The IIMs do cater to this somewhat, but not to the perhaps level of detail that is required. So speaking of climate action, we can think of it as falling into 4 broad paradigms. So on the one axis, we have mitigation versus adaptation. On the other axis, we have short-term climate action versus long-term climate action. And examples of all 4 paradigms are given here. For example, if you think of renewable energy, which would mean solar, for example, then it's a long-term mitigation climate action. Similarly, when we are thinking of alternate fuels like green hydrogen, for example, where we have to set up the infrastructure and so on. So it's a very long-term projects. The short terms you could think about, for example, carbon capture, utilization, and storage, improving energy efficiency of processes, of industries, of buildings, which would also count as short-term mitigation. And on the adaptation side, we have urban planning, we have agriculture and food security. And again, on the adaptation short term, we have to deal with actual climate impacts, which is extreme weather events and so on. So we have disaster response, coastal protection, and flood management. So we can see that there are lots of climate actions to be taken, but the only perhaps realistic way of going about this is to model it very carefully. So if we want to successfully deploy climate action policies and take effective decisions towards climate mitigation and adaptation, we need, first of all, a proper modeling platform and robust data analysis. So that's basically where we come from. It's our motivation for the next couple of slides. We are actually developing a modeling platform at the Energy Consortium called the Climate Action Tool. It's along the principles of IIMs, but catering to the kind of disaggregated requirements that I mentioned earlier. So it is semi-empirical. It's based on real-world data that we can collect from as many resources as possible, public data sets, etc. It is parameterized, and it also has an optimization engine. So we can give it, for example, questions such as, how do you optimize this particular policy so that my GHG emissions are reduced 10 years from now? So that's basically the goal of why we are developing this platform. Just a brief, to go into the working principle of it. It's a hierarchical platform. So you can model a single individual process which takes an input resource, transforms it into an output resource, or scales it up through some transfer function. So that's the one in panel A. You can then chain multiple individual processes to create a sequence, in which case you would be able to model a factory or a plant. And when you put together enough plants or factories, you get to the industry part, because you have multiple plants together. And then finally, you have, when you put multiple industries together, you have a cross-sector model. So it works in a very sequential, hierarchical fashion. Now we've been able to, so here is a snapshot actually from the tool itself. So we're looking at one very specific sector, which is cement. You can look at all the different processes that exist in cement manufacturing, and it takes input resources like limestone and additives, etc. And on the output, you have the cement on the extreme right-hand side. So when we do this modeling for additional sectors, for example, cement, power, and steel, I mentioned cross-sectors. So when we put all of these three together and we ask a question like, for example, what should be the fuel mix for each of these industries, so that both cost and emissions are minimized. Similarly, you can ask another question: should you actually capture the CO2 that comes out of the cement industry? If you have to capture it, then would you convert the captured CO2 into gray methanol? Would you convert it into green methanol, or would you sequester it? Or, right? So these are some typical policy questions that you can ask. And the tool actually helps us figure out how to answer these questions. So on the right-hand side panels, you actually see histograms. So these are optimized results. Of course, this is a very preliminary, simple model, but in practice, it works. So you can see that in the panel B, we have the distribution in cement, steel, and power sectors, specifically the distribution of the fuel that you're supposed to use in the for each of these different sectors. And we can see that for each sector, the fuel actually varies. So for cement, the suggestion is that you still have to largely rely on coal, but for the power, you can already see that the platform, the modeling platform is saying you can actually switch to renewable already, because your prices for renewable energy are quite close to parity with prices of non-renewable electricity. Similarly for panel C, so cost increase versus emissions reductions, we can see what percentage of the cost is increased, because at the end of the day, when you want to reduce GHG emissions, it is going to cost. Either you deploy CCUs, or you're going to change your processes, and in which case they become more expensive, or you change your fuels. So the panel on the right, the C panel, shows what is the cost increase for every sector if you want to reduce my GHG emissions, and for that particular cost, what percentage of emissions reduction can I actually accomplish? And that too varies with sector. We can see that it is actually the power sector where just for about 25% of your cost increase, you're able to retain close to 90%, 95% of emissions reductions. And similarly, the tool also provides an optimized result for whether we should capture CO2. And that too varies with the sector in question. Now, this is, of course, to create new policies. We can also backdate or work with existing policies. So we have this Perform, Achieve, Trade scheme that was released by the government of India. It's a scheme that was designed to promote energy efficiency or energy savings in the industries. Now we can see whether the targets that were set by the government were actually adequate, were they inadequate, could they have done better, could the industry itself have done better? And the answer is theoretically, yes. We can see the last plot there, where on the y-axis we have total energy, million tons equivalent. And we can see that compared to the targeted reduction, the potential to save exists a lot more. And the same holds for the CO2 emissions as well. Now, these are conventional modeling methods. The question, of course, is how can we augment this with AI and ML? And this is something that we are actually working on. It is something that we are exploring. When we want to use AI for modeling, there are, of course, lots of challenges and fields that we have to take care of. First is data collection. So because we are using a modeling and we use semi-empirical, I mentioned before, the data has to be collected from somewhere. Typically, it is public data sets, and if it's one of the big companies, then they release public reports from which we can collect. But if you want to do this for 1,000, 2,000, 3,000 companies, it becomes quite tedious. So we kind of need to automate this process. So there are a couple of ideas that we can explore in this regard, which is you can use large language models to read reports and automatically parse data for you. And where you have plots, for example, and we need to recreate the data, for example, this is, to my knowledge, there is no known artificial intelligence method that can automatically extract data from plots. So this is kind of a deeply felt requirement. So we can explore deep learning for deep learning methods, convolution neural networks, etc., for object detection. So given a plot, please produce the table that gives rise to the plot. So there are some ideas that we are working on with our researchers. Then in energy transition, again, we have support vector machines or classification for the energy market behavior. So we have specific events where your energy demand goes up or energy demand goes down. You can sort of classify that so that the operator or the grid operator knows how to schedule those things. And then we also have predictive analytics. So how much is my demand going to go up or supply going to go up, for example. Then we have energy efficiency, LCA analysis. So when we think of modeling, we also want to find out what is the impact on the environment. And when we try to model this, we try to optimize this, we often have to deal with decision variables or binary decision variables even. So here one idea for using machine learning would be to deploy decision trees to validate the models that we develop so that whatever we use, the modeling platform, whatever we optimize and we get, we can validate that with decision trees, provided that we have the requisite data needed for that. And finally, we have GHG emissions. So we have recurrent neural networks for time series forecasting of emissions. And another major area, I think there are several publications that are, several research publications on this particular field, which is using convolutional neural networks or some sort of deep learning based algorithms on remote sensing data to track industrial emissions and land use change. So these are areas that we are still working on. And just one particular application that we found seems to show promising results is where it comes to energy efficiency. Here is an example problem where we want to detect the heat transfer coefficient using AI and ML. So since I'm short for time, I won't go too much into the details. But traditionally, these are done using correlations that are collected from experimental and then published. And we wish to see how good AI and ML algorithms perform in predicting these heat transfer coefficients. And we can actually see the green dots here. So on the x-axis, we have experimental heat transfer coefficient. On the y-axis, we have predicted. So the red line is the 1:1 slope 1 line. So dots on the line basically mean our machine learning algorithm is doing well. Now, the purple dots are theoretical correlations that exist already in literature. They have been published long before. And the green dots are the predictions of our machine learning model. So basically, we can see that they are a lot more tightly constrained than the existing correlation. So it seems, at least at face value, to be performing better than the theoretical correlations. And this we compare for two different correlations at two different regimes. And we get fairly similar results, promising results. And with that, I think I would like to close my talk.
Thank you very much. Okay, I'll take one or two quick questions from the floor, please. Okay. Oh, there's one online apparently. I can't see online at the moment though. I wonder if somebody could grab the microphone and read it out for me, please. Maybe we can have a look on your computer.
Yes.
We possibly can.
It's just a comment, I think.
Okay. So the comment is, good session, very clear. Congratulations. Okay, so I'm wondering about the graph reading that you're doing there with deep learning. What's the way forward on that?
The idea I have is definitely to use synthetic data. So you use existing tabular data, plot it, and then a combination of cross correlations with images. But I suspect that would not be enough. So we would have to train deep learning convolutional neural networks to first to identify the axes, and then using a loss function, try to find or retrieve the tabular data back from the plots again.
Sounds very sensible.
Yeah.
Okay. Okay, I'm not seeing any more hands up, but before you leave the stage, we do have a small gift for you as well. Okay, congratulations. Okay, our next speaker is Jayesh on data collection issues and challenges from commercial establishments for implementing net zero, but I believe we've also got Jagjit as well, who's coming to the stage in person. So I'm not sure whether you're doing it in combination or who wants to go first.
So we'll be presenting in combination.
Fantastic. Okay. Okay, it's all yours.
Hello, everyone. My name is Jagjit, and I am a MS student in Applied Mechanics department. I, along with my colleague Jayesh, who is from Energy ETA, IIT Madras incubated startup, we'll be talking about the data collection issues from commercial establishment for implementing net zero. So we'll be talking about net zero and what does net zero means in commercial buildings, the IoT use cases in commercial buildings, and what are the challenges and possible solutions in collecting the data. So I will request my colleague Jayesh to take over from here and cover some part of this talk.
Sure, Jagjit. Am I audible there?
Yes.
All right, good afternoon, everyone. I think we are in the middle of lunch and last part of this session. So we'll try to be on time. So as you know, in our previous talk, what we heard about, ability to estimate using a climate action tool, what kind of possible scenarios exist to achieve net zero goals. This talk will go bit depth into the machine learning piece and specifically the issues associated with the data gathering, as Jagjit highlighted. So before we do that, a little bit background. Net zero, as most of the audience is aware here, is something about balancing how much we are producing and much we can remove. And one of the key contributor to that turns out to be electricity. Apart from producing material and food, also contribute to greenhouse gas. But the electricity, if you look further into it, next slide if you go, Jagjit, is ultimately the single most important parameter which we would like to control. So top left chart, what you see here is not meant to be read, but what you see there is the increase in CO2 is linearly correlated with the temperature rise. And that has happened last 30-40 years, much more prominently than the typical cycle. So it is no more a if and else question. It is the reason for increase in temperature. It has been established. We are about 423 part per million as of this year, the CO2 concentration, which is way above typical 370-380 average, which we have seen in centuries. If you look at this is a recent report from MNRE that if you would like to achieve as a world the net zero goals, we have different targets for different countries, but one unified suggestion or approach which has been recommended is there are total 6 initiatives which has to be taken to be able to reach net zero goal. And if you see the top two, the renewables, we heard quite a few topics about it. The second is about energy conservation and efficiency. Third is electrification in end user sector, the hydrogen and its derivatives, CCS, carbon capture, which I think also we heard partially. And the last one is again related to BECCS, again related to carbon capture technology. So those are under development. So if you look at the top three, the second one, energy conservation and efficiency, turns out to be very important lever, which has not been given equal importance. That is what we as a group are focused on right now. Now, if you look at locally country, as a country specific, again, not many guidelines on energy conservation and efficiency. Those are being taken up now by Ministry of Power in India to promote the energy conservation and efficiency. They are coming in the form of building code. Now look at the growth story of commercial building. That's the specific interest for our topic. We move next, Jagjit. So our country, where we are currently doing this, event along with UK university, the India turns out to be having the growth path for buildings highest in terms of year-over-year growth, and 2.7 compared to China, Africa, any other countries, it's much higher. What it means is, simply putting, we are going to add very high number of buildings in next decade itself, and that's all going to be air conditioned. So that brings us to the topic of how can you do this, in right way. Next chart, if you go, it talks about inefficiencies in buildings. So these are different sectors. What you see here is EPI, Energy Performance Index, how much unit you consume per unit area of building in a year. And you can see here a clear trend. Industries are much ahead. The manufacturing plants in terms of energy efficiency, lower the number is better. But the hotels, malls, commercial buildings, offices are having almost 4x inefficiencies in their energy utilization. So how do we solve this problem? We go to the next slide. What we need to look at is now building as a system. So if you look at a typical building, you see here, these are the systems which you will see starting from ventilation, air conditioning, chillers, heating, heat pumps, boilers, the air quality measurement systems, then energy power quality improvement. Now all this as a system, if you look at, they are all independent systems, but they all contributing to the journey of net zero. And the one thing which can combine these systems operational efficiency is the application of artificial intelligence, and in turn the data. Here are some areas where active work is going on, which leverages data and AI, forecasting of what if will happen to my energy consumption, and ability to do proactive actions, ability to detect anomalies in the sensors, in the machines, and help them remain efficient, ability to simulate the various equipment scenarios using digital twin, again required a significant amount of data and physics to be able to simulate. And the last, not the least, is the optimization. So each of these systems are mechanically connected, but not in a brain wise. There are different brains in each controllers of a chiller plant or air handling units, pumps. If you take them together and optimize, there is a huge opportunity to save as high as 30% energy. So that's what this commercial building opportunity is. If we are able to reduce one building waste, it's an estimate that about 1,000 houses you can power. So that's the impact the building energy conservation can bring. So these are some of the stakeholders in a building. So when we talk about building and data collection, we need to be cognizant there are three stakeholders in a building. One is the facility managers, the key ones, who are in the middle of guests, patrons, and the owner, who is the one who is going to pay for any green investment to decarbonize its building. So there is a significant amount of investment, as we heard in the previous talk, required to decarbonize, but saving energy is almost the highest ROI you can get. So go to the next. You can move on. I think we can skip this. So this is the typical cycle of a machine learning application. Any of the application, if you do anomaly detection or forecasting or optimization, and one single key word which is common and which is foundational is the data. And collecting a data from a building which is as varying as what we saw is in itself in challenges. So I will just invite now Jagjit to walk us through some of the challenges we have encountered and what kind of possible solution approaches which exist. And some of those we have already applied. In the interest of time, we may not go into depth of each one, but we'll give you a good overview of the different challenges associated with it. Go ahead, Jagjit.
Thank you, Jayesh. So as mentioned, I'll go to the practical challenges that we face during the data collection from these buildings. So first of foremost is when we go to data collection, there are a lot of different type of data types that we see in a typical building. For example, some of them are binary, that's true, false. Some are analog, that is continuous data, and some are multi-state, that is basically a classification type of variables. So each variables need to be treated separately, each need to be aggregated separately. So there we need up somebody who has industrial knowledge and tag this each variable and how we have to treat each variable in a different manner. So, and second part is, since this is an IoT-based system, the foremost problem in an IoT-based system is the connectivity. So most of the time when there is no connectivity due to maybe several reasons, there is a issue of buffer data. The IoT device will keep accumulating the data inside its memory, and then then this data will come to your cloud at a later stage of time. So you have this issue, and now how to tackle this previous data. Also, like, the device will have this dilemma. The device, since the connection is now restored, the device also need to send the live data. So now what should we do? Should we send the buffer data first and then live data, or should we send live data or buffer data? So this is the dilemma, because you will be losing the live information if you are just keep sending the buffer data, because the IoT devices have very small memory and small processor. It takes time. It is capable of sending just one packet at a time. So there are few solutions, like we can do send alternative packets, like 2 live data and 1 buffer data. So like during the course of time, the buffer data will get eliminated from the device and will push to the cloud. Other problem is the sensor placement. As we have a very wonderful talk today about the sensor placement, so this is actually a very concerning issue. So the same sensor can give you very different values at nearly very 2 different locations within the same premises only. And it is very essential that our sensors are placed at the right place, where that is free from the contamination of, let's say, if there is a temperature sensor, it should be away from existing machines, so that the values, for example, if it is capturing the ambient temperature, it captures it correctly. Moreover, we can have efficient strategies. For example, instead of putting a lot of energy meters across the buildings, we can have one single energy meter and have different parameters across different places that can be judged to establish like which machine is working or not, and based on that we can actually determine the energy consumption of each component. And third most is the sensor anomalies. We would want to have different type of algorithms on top of our data collection pipeline that will essentially tell us if the sensor is performing well, if the data is drifting or not, if the values are making sense. So the other point is data aggregation. So this is basically the data that the IoT sensors will send you will be the raw data. Getting the information out of raw data is very difficult. So you need to have some kind of mechanism to extract information. The most efficient way is to just aggregate it on certain intervals. it can be hourly, daily, monthly, like that you can, so that you can have a gist of the information, what the data is saying from you. And again, so there are a lot of problem in this approach as well. As I mentioned earlier, the problem of buffer data. For example, if you are aggregating the data that is coming today or the last hour, at every hour you are running your pipeline, but again, now you have the problem of buffer data. Now, the one layman solution is to aggregate the entire data. For example, you just have a threshold of 1 week. You're saying, okay, my data will, the buffer data can come almost 1 week old, not older than that. Then you can re-aggregate those of 1 week data. Okay, sorry. So, and then other smart solution can be to only aggregate the affected pipeline, affected period. For example, if you get the data of yesterday, that hour, you just aggregate for that hour and consequently that day and that month. Other problem is the data relationships between the machines. For example, if you are calculating the IKW per TR or COP of a chiller, you might also need the energy data that might be coming from another sensors. But at the time of calculating this COP, you might not have the data from the energy meters due to several issues. So that issue can be resolved by establishing dependencies between the machines. So for example, when the aggregation happens, the parent machine, for example, in this case, in this example, the energy meters are the parent machines, that is aggregated first, and then the dependent machines, for example, the chiller, that will calculate the dependent variables that will require the data of parent machines will be calculated next. So in this way, this problem can be handled. Other problems in data collection is the lack of variations. For example, if we want to train a model, our model should have a lot of variations of data. In typical building, the most of the chillers or most of the equipments runs on a same setting throughout the year, maybe slight variations. But in order to develop a deep learning model, it needs to know the non-linear behavior. To learn the linear behavior, it needs to see the range of variations. So some way to tackle this is you can do this sequential scheduling of various equipments, random scheduling. You can integrate physics-based model and change the set points to other values that are being defined by the machines. The other problem is lack of standardization. So we work with a lot of companies and a lot of equipment manufacturers. The problem with them is that they have their own set of nomenclature for each the same variable can have different names across different machines. So these problems actually actually is a very big problem in terms of standardization. So there are certain solutions that are actually emerging in the market. So one such is the Project Haystack. So they intend to standardize the naming of these variables across the domain so that the data interoperability between the models can be attained. And the other problem is cloud cost, effectively. So these can be linked to the data granularity. If you are sending data at a certain frequency, slightly changing the frequency can change your cost to a great extent. And last problem is the data ownership. So there is a lot of ambiguity. Who owns the data? Is it the building or the company that is capturing the data? And also the guidelines are not clear. The guidelines in the EU can be entirely different than in India. So this is another set of problem. So I would like to conclude my talk. Thank you very much.
Thank you. Okay,
Yeah,
we
happy
do
to
have
take any
time for
questions.
a short question, please. Okay, straight with the hand up, just over there. Bhupesh.
Hi, I'm audible? Yeah. Thank you for your talk regarding these data collections. So I believe the sensors you are talking about or you're working about is a low-cost sensor, right? is it low cost sensors, or you're working with low cost sensor, or medium cost or high cost sensors?
So it's a range from low to medium cost sensors. Yeah.
Okay, in this regard, Narman, the literatures and others are saying that, okay, so when you have low cost sensor, there is always a drift in the sensors. So have you considered that parameter? Because I see the 7 challenges, and probably I didn't see or I might miss that there is drift in there. So how you handle drift in sensors?
So basically, drift doesn't come instantaneously, but once you go to the site and deploy your sensor, you first calibrate that sensors with the actual data that you might read through on the BMS system or the other analog systems that you have. So once you install those sensors, just during the course of time, the drift will come. For example, in a year or so, you'll then see the relationship between the data that was coming earlier and data that is coming now. So that is how you establish the relationship that the drift has come in that sensor, and you go about and correct it.
So that's a follow-up question. So how to confirm that whether this is a drift of the sensor, or there is a changes in the environment or condition, or constraint has been changed of the building?
Correct. So you have a lot of APIs available that actually captures the ambient data of that particular area, and you take into account those APIs also, those values, parameters also. For example, it could be like the actual temperature of that area has increased so much that the sensor is actually making sense. It has not drifted due to maybe global warming or other effects. So that is something that we have to include in it.
Okay, there is a question from Sam online about building materials. We seem to be stuck more on building rating measurement or broad concepts like digital twins, go upstream and solve supply.
Almost no low cost or locally manufactured supply. I think it's a comment than a question.
Yeah, I think it's more of a comment as well. But if you wanted to reply to that, maybe you could do so offline, perhaps.
Jayesh,
and there's a question there about getting the recording of yesterday's session, which I believe is a yes. And I'm looking towards Devika and colleagues to see if there is a comment that we can supply a link there, please. We do have a small gift for you as well. So if we can get hold of that, please. Okay, congratulations and thank you so much. Thank you. Okay, our final speaker of this morning is Nina, and she's talking about conversational AI in offshore wind. Nina, good morning.
I am. Hello. Yes, it's morning here. It's funny, you're waiting for lunch, isn't it? I'm kind of in the way of that now. Let me try and share my screen. Hopefully that will work. So if I move the slides, can you see that?
Yeah, we can see your slides. We can see you clicking.
That's a good thing then, isn't it? Okay.
Okay, over to you, Nina. Thank you.
Okay, cheers. Right, yes, conversational AI and offshore wind. So yeah, that's just to introduce myself. Oh, it's very quick now, isn't it? Yeah, okay, let's go with this. So yeah, I'm currently a reader in computer science at the University of Hull. I lead a research group in big data analytics. So much of the work that I'm going to talk about was done by some of the people there. I'll have a picture later. And this is sort of how we got started. So that was work done by my PhD student, Georgit Chatterjee. He started around 2018, so 6 years ago now, and that was one of these things that he started with. So just trying to see how much AI there was actually in offshore wind, and whether it was novel enough, essentially. So what we can see is there was a lot of signal processing approaches. So this is mostly to the task of operations and maintenance. So looking at wind turbines, predicting when they're going to break, what is going to happen, and how can we fix it? And we can see that since 2017, there's been this sort of sharp rise in methods that apply more artificial intelligence, neural networks mostly, but also other approaches. So it seemed to be the way to go. And the other thing that we looked at was this kind of thing. So specifically, in terms of AI, what methods are being used. And one of the things we see here is a lot of explainability. So we see these XGBoost models being applied more and more. So neural decision tree classifiers essentially. And then we have all these attention bits. So LSTMs with attention, CNNs with attention. So it seemed to paint quite a clear picture about people wanting explainable methods in wind. I guess if you're an offshore wind operator or owner or something, you just don't want to make high stake decisions based on, I don't know, some AI and a confidence level without understanding really what's going on. So this is what we wanted to develop. And this is kind of just an illustration of the problem. So you will have come across SCADA data by now. So the mechanical, electrical readings of wind turbines, and then a combination with environmental variables, wind direction, humidity, whatever. You can forecast these kinds of things that we're interested in: alarms, maintenance actions, and so on. Now, the interesting problem is more this kind of evolution almost of offshore wind for us. So there's lots of data at the moment available for these kinds of turbines. So earlier generations of turbines, monopiles. You can see the shore here, so they're all quite close to shore. Also, offshore is reasonably available to do data analysis with. But if we're looking at the colleagues in engineering, they're much more busy building these kinds of turbines, obviously, so much further out at sea, where the wind speed is much higher. And it's quite important we do that too in order to reach net zero. But obviously for these kinds of turbines, we don't have data available. So it might be patchy. Sometimes we might have some, or sometimes we might just not have any data at all. So it becomes an interesting kind of transfer learning problem. And that's one of the things we wanted to address. And then the other thing we wanted to do, so my original background is in natural language processing. And I wanted to see, can we do some language processing here in order to provide decision support? So specifically, if you have a scenario that you don't understand well, maybe because there's data involved that we haven't seen, or maybe there's a scenario where we just don't have much data, what can we do? And we had a data set given to us by the Catapult, for those that are aware. So it's essentially a demonstration turbine that have all these sort of little cryptic messages here explaining the SCADA data. So we have things like wind speed above max start, we have demoted, yaw brake fall 2, under pressure full brake. So, and I'm sure for the people that work with the kind of data on a daily basis, that makes a lot of sense. But if you're in a situation where you don't work with the data on a daily basis, or maybe you're under training, or whatever, I think it could be better. So what we wanted to see is, can we use these kinds of messages, maybe in combination with the SCADA, and again, the weather data, and make it a bit nicer. So that was one of the first experiments we did here. And that was, I'll get to the experiment, but it seems, I'll talk about the architecture first, sorry. So the general idea is here, can we take SCADA and actually apply something like data to text generation to explain it? So to interpret the data, to explain it, and then maybe explain it to different user groups. So for example, the person that sits in the control room and needs to make decisions about, sending a vessel out for maintenance, or shutting down the turbine, or what is the best course of action. Also for somebody who's maybe about to go out and give some maintenance to the turbine, or maybe somebody who's writing a business report. So there's all these different users with all these different needs. And something like AI or data to text generation seems quite suited to tailor to these needs. The second thing is information extraction. So lots of industry sectors, offshore wind is not unique in that regard. They've got lots of data, lots of knowledge hidden in documents, reports, logs, technical documents, whatever you have, but it isn't normally quickly available. So as you're sitting in the control room and making these decisions, you don't normally have access or time to browse through these documents and find the information that you need. So can we use information extraction or even information retrieval to facilitate that, to accelerate it, essentially? And then ultimately, can we package it all up into a conversational AI system that allows us to do that quite interactively? So that was the vision. And here's some sort of architecture. You've got some kind of data. It could be images. It could be text. I've spoken quite a lot about text. So it could be some other sort of formal knowledge representation. You've got your data to text module here, for example, and then you've got some user that in this initial architecture is just a passive recipient of information. So working up from this, we then really want the human to be a bit more active, because that then enables us to create this interactive decision support scenario. So where the system says something to the expert, but the expert can then respond back and maybe help us, optimize key performance indicators over time, and really just enable this expert in the loop continuous learning scenario. So this is the kind of thing we have in mind. With this, the system might detect something. Okay, so this might be a SCADA feature, intermediate stage gear vibration increase detected. This can happen when there is an issue with the intermediate stage gear bearing. So kind of explaining it, it's probably correct, but it's also just restating the feature name, isn't it? So what we'd like is a scenario where the expert can say yes, so sort of confirming that it's okay. Or it could also be an intermediate stage tooth issue, so offering this alternative explanation that gets added to the knowledge base, and then we sort of go from there. And then we can plug any kind of fault interpretation a fault prediction kind of module. Lots of people work on that, so that wasn't something I want to talk about today. Anything can go into this. So so that's the setup. I'll talk you through our first experiment. So we built two modules essentially, a binary classifier that just says, based on a SCADA sequence, is that fault pending, yes or no? Okay, so binary. And then if the answer is yes, it will try to predict the maintenance actions that would address the fault in some way. So the sequence of outputs essentially. That's harder because it's a sequence, obviously. On the other hand, we then have the template. So we use these little cryptic messages that I showed you as an example, but we made them a bit nicer. So from 102 SCADA features and 26 different alarm types, we had to write 167 unique templates. And then you get this sort of thing. Okay, so a yaw misalignment is affecting the turbine operation. High and variable wind speed is affecting the stabilization properties of the yaw brake. A forced shutdown is recommended until the absolute wind direction returns to normal. So it's a lot nicer, I think. It's a lot more complete. I think it would help in things like training and people that don't fully understand what they're doing already, or that just don't have the context always. But we didn't like it. So in terms of the alarms, the model works reasonably well. So this binary classifier gets 97% of accuracy, but frankly, most people in the literature do, because it's just not a very hard problem. Okay, so that's not where the specialty is. Maintenance actions, so this sequence of things that need to happen to address the fault is just 75%, which probably is not very impressive. So if you wanted to apply that in practice, 75% is probably not good enough. The templates need to be handcrafted. So thinking of this transfer scenario, if you've got floating wind or any other sort of structures, it's likely that we need to redo the template. So it's a lot of work. And then from a research point of view, it's also just not very interesting if you have to write the templates, I would say. So that's not great. So that was the question that we asked. Can we get the language automatically, essentially? Yeah. And that became George's lockdown project at the time. So he went through all these documents online, anything open source, essentially, that he could find on wind turbines, and came up with his knowledge graph. So this is just a small part of the knowledge graph. It's a big thing. But this is, so for example, this is the bit about the drivetrain, one of the components of the wind turbine. Drivetrains have main shafts, okay, and they have all of these. These are preventative maintenance actions that are associated with this component. So you can then query the graph, which is useful. But the other thing is, and that's the sort of real nice thing about it, is you can reason about it. So that means when there's an area that you come across where you don't have data, as long as the turbine has similar components, it can still sort of give a reasonable output based on the reasoning of what it has in the knowledge representation. So I think it transfers better, and it is reliable, because you can inspect it and see exactly what it did and why it did it, and it can explain its output. So that's, I guess, where the responsibility comes in. This is how we train this. So you still put SCADA features into it, generator temperature, gearbox temperature, and all of that. Okay. And then we had this parallel data set. So natural language questions, something that somebody might ask in language, and then mapping it to cipher queries. So formal bits of language that allow us to access the knowledge graph. And this is essentially a data augmentation phase. So generating paraphrases from this data set just to account for the fact that you can, language is ambiguous. You can ask the same question in many different ways. And then we train it here. So it's just a transformer that translates one sequence to another. So just as you might translate English to German, you might translate a natural language question to a formal bit of language. And this is the applied scenario. So if this is training, this is now how we'd use it. So an end user might come, again, imagine your operator maybe, and might say something like, what are specific corrective actions due to an inconsistency in, and then there's the feature name, wind turbine, rotor speed, standard deviation. This gets translated to this cipher code, which is nice because we can do two things. We can quantify the accuracy of this, so we know exactly how accurate the model is. You can't do that if you're sort of doing language to language, right? And the second thing is a human could inspect the cipher code and ensure that it is indeed what they wanted to know. And if that is the case, we just, retrieve the answer and it's going to be correct. This is the results from this. So it's a bit better. It's 90%, but it now includes maintenance. So it's come up from 75%, which is a bit better. And it's a bit more practice near, maybe. Okay. So that's the real project I wanted to talk to you about today. This is part of a collaboration I'm currently doing with the Catapult and multiple wind farm owners and operators here in the UK. So the pilot was successful. I declared it to be successful. So what we're currently trying to do is embed this in practice and seeing who wants to help us use it, and we can do that. Other projects in the space. So one of my other PhD students, Callum, he did an internship with Toshiba where he tried the same kind of idea of this interactive learning. So an expert sitting in the loop and guiding a learning algorithm for structural health monitoring. So that was looking at drone images of damage on the turbine blades and then learning to label that damage. And you can see if you have people that know what they're doing, you get a nice sort of steep curve upwards. And that means we can sort of do that quite efficiently without having too much data available. And then the final bit is that was a collaboration with Germany. So that was an award that Joyjit won for the work that I've presented. So he got to go to Germany to detect ice on wind turbines. This is the CDT that this is all part of. So the Aura CDT, I don't know if you've spoken about it at all. It's essentially a center for doctoral training that we have in Hull. We've just been renewed until 2032. So that's good news. And I just wanted to acknowledge that. And then finally, this is the people that did the work. So this is Joyjit. He did most of the work that I've presented. This is Callum. We've probably come across Eamon. He's also working in that space. And so that's the group. These are the people that do the work, and you can see the funders on top there. And that's me done. Thank you very much.
Thank you. Okay, we'll take some questions from the floor, please, or if there's any online. Okay, could we switch to the online, please, so we can see it? Okay, thank you. So, Nina, having managed offshore production gas and oil platforms and drilling rigs in the North Sea, a lot of work with SCADA-based systems in oil and gas with Gen AI bots for data interface from Sam. Probably more of a comment there, Nina, but I don't know if you want to respond.
It's more a comment, isn't it? I think I think it does transfer to oil and gas. There's similar work in Edinburgh in Scotland that they have the same kind of infrastructure that we have in offshore wind. They do this for oil and gas, so I think they work with similar methods. Bots are interesting, maybe more as a collaboration tool than autonomous, but yeah, it's good.
Okay, Nina, I wonder if I can ask you to stop sharing your screen, but keep your face online, because we do have a small gift for you as well. And I'm going to invite Koorosh just to come to the stage to accept on your behalf, if I may, and we'll find a way to get that to you. Koorosh, do you want to come up?
You've got me really big there, isn't it? It's terrible.
Yeah, absolutely. So let's see. Can we get the? Yep, just on its way. Okay, so Koorosh, you've got to get this to Nina, I'm afraid, but congratulations. Thanks, Nina.
Thank you very much.
Okay, and that concludes this morning's talk, and indeed all the talks. Can I ask the people online and indeed in the auditorium here today just to give a round of applause to all the speakers this morning? I'm sure you'll join me in saying that there was absolutely a wonderful experience. Thank you. Yes. And I'll hand back at this point.
Yeah, so hello everyone. Thank you, Professor Kevin, for handling the session. And with that, we have actually come to a close of the two-day workshop. So I would like to mention a few gratitude at this point before we go for the photograph. So first and foremost, yes, of course, to our organizing chairs, Professor Balraman Ravindran and Professor Dhaval Thakur. Both of them are not here at this point, but I really thank them for their guidance and organizing. I thank the entire team of Hull University who made, can you please all put your hands up? I can't mention all your names, so it will take a long time because it was a big contingent that flew all the way from UK and unfortunately had to attend the first day of the workshop online from their hotel rooms. But thank you for being patient and also taking the major load of the initial process of registrations, the reviews, all those organization part. Thank you, the entire team of Hull. I would like to thank the track chairs, Dr. Will Jones and Professor Satya from here, thank you, and Professor Nishikant from Hull. Big thanks to Devika and Bhupesh for handling the local coordination part. So thank you, Devika. Special thanks to you for taking over when I was sick last week. And I especially thank all the keynote speakers. And yesterday, Mr. Raghu Dharamraju made the trip almost halfway to the Bangalore airport and had to return back because of the warnings of bad weather. So special thanks to him. And thank you, Sandeep sir, for making the trip and delivering the talk. And special thanks to Professor Amit Seth for delivering the online talk from a different time zone. I thank all the invited speakers who delivered very good and insightful talks. I thank all the panelists during the panel discussion yesterday, which was really amazing. Apart from that, there are a lot of people who did the groundwork here and made it possible. I thank Chief Operating Officer, Mr. Sridhar of RBC Desai and CRI. I thank the vibrant team led by Suganya and Soundarya here at RBC Desai. I thank the support team of ICSR, NPTEL, and all the tech team and venue team support staff. Thank you so much. And there was a lot of tech support that required yesterday because of the online. So they were up and helping us through phone. Thank you so much. I thank all the reviewers who reviewed the papers for us. So a big shout out to them. I thank the volunteers and post-bac fellows of RBC Desai and Sirai who helped us. And finally, I don't have to thank my fellow colleagues, but I have to thank like Sanjay, Vidya, and few others, and also the admin team, which I shout out to again, because without them it wouldn't have been possible. So thank you all. So if I have not mentioned any names, kindly forgive, but I thank all the people who have supported with this event. And finally, the participants. Thank you for showing up today. Even though it's just half full, I'm really happy that all of you are here and we could actually meet you in person. So thank you, everyone. With that, I close the workshop session.